This video explores the relationship between two continuous variables. Here we will cover fitting a linear regression model to predict the dependent variable and interpreting the results. Let's consider the following case study, where we want to explore the relationship between two continuous variables using simple linear regression. The following dataset contains information on housing prices and distance to the nearest public transportation station in the Philippines. This is a sample dataset illustrating potential trends for regression analysis. Before estimating a linear regression model, first, quickly gain an understanding of linear versus nonlinear models, estimation methods, statistical assumptions, and validation procedures. A model is considered linear if there is a linear relationship between the dependent and independent variables. These are some examples of linear models because the partial derivative of the dependent variable is independent of the parameter. In contrast, a nonlinear model captures more complex relationships that cannot be represented by a straight line. For example, the following models represent the nonlinear models. Several methods exist to estimate regression parameters, including maximum likelihood, least squares, and method of moments. The least squares method is the most widely used due to its computational efficiency and ease of interpretation. We'll focus on this method for parameter estimation. Now, before estimating a linear model, we need to ensure that certain statistical assumptions are satisfied. The main assumptions include the linearity between the independent variable and the dependent variable, the independence of errors, the homoscedasticity, that is the equality of variance of the errors, and the normality of errors. Any departure from these assumptions affects the validity of the estimated model. Let's proceed with the case study using Excel's data analysis ToolPak to perform a simple linear regression analysis. This method is suitable because our linear model only has one independent variable. To do that, first, open an Excel spreadsheet and create two separate data columns for the housing price and the distance variables. Now go to the menu bar and select the Data tab. In the Analysis section, select the Data Analysis ToolPak, then click on Regression. Now in the pop-up window, go to the Input section and select the variable Y range and the variable X range. Check the box for labels. The default confidence level is 95%. Select a cell for the output range. Check the box for residual plots, the line fit plots, and the normal probability plots, which will be used to validate the regression model assumptions. The output summary of the regression analysis is obtained. Now, we will use the regression output summary to interpret the key results and validate the regression model assumptions. The least square estimate of the regression model equation is y equals 5.1886 minus 0.0016 times x. The model predicts an average house price of 5.1886 million pesos when the distance to public transportation is 0 meters, which is unrealistic. This emphasizes that the y-intercept likely doesn't have a practical meaning in this context. The coefficient of minus 0.001554 indicates that for each additional meter away from public transportation, the expected price of a house decreases by an average of 1554 pesos. The t-test for the slope coefficient has a p-value less than 0.05, which confirms a statistically significant relationship between house price and distance to public transportation. The R-squared value of 0.9359 suggests that nearly 93.59% of the variation in housing prices can be explained by the linear relationship with distance to public transportation. The standard error of 0.2143 million pesos indicates that on average, the actual price of a house can deviate by this amount from the predicted price based on the distance to public transportation. Now, we will validate the regression assumptions based on the plots. The line fit plot suggests a linear relationship between the variables, supporting the linearity assumption. The random scatter of residuals around the zero line in the residual plot validates the independence of errors and homoscedasticity since there is no funnel shape. The normal probability plot with a diagonal line implies the normality of the errors.